Lecture series on testing of VLSI circuit. In the previous video, we saw about various types of fault. In this video lecture, we can see about the fault diagnosis method, the path sensitization method. It is the process of assigning the appropriate logic values, either 0 or 1, to all off-path inputs so that the effect of fault can propagate from the fault side to the primary output without being blocked. Let us consider an example circuit with three inputs and single output, which has all types of gates like NAND, NOR, and inverter, etc. Let us consider a scenario where stuck at zero fault is occurring at the input X1. If this is the case, how a path sensitization algorithm is applied to the circuit? This is what we are going to discuss in this video lecture. So, coming on to the various steps involved in path sensitization, the first step is to select the fault propagation path. Here, if you look into the circuit, though there are many paths from input to output, for example, for X1, it is through G1, G2 and G3. The another path is through G2, G3, X3 through G2, G3. Another path is X4 through G4, G3, G5, G4, G3. So these many paths are there, but the fault propagation path is G1, G2, G3. So next is to assign a non-controlling value to the off-path inputs. Here, once the propagation path is selected, which is nothing but G1, G2, G3, the off-path is nothing but other paths that I have mentioned. So, what is non-controlling value? For an AND gate and NAND gate, AND gate is a gate which produces output 0 when any one of the input is 0. So, 0 is the controlling value. 1 is non-controlling value. Similarly, NAND gate, if any one of the input is 0, output is high. So again there also 0 is going to be the controlling value. 1 is going to be the non-controlling value. So similarly for R and NOR, non-controlling value is 0. So inverter, it is no off-path input. So based on these gates only, all the gates are going to work. So we have to set the non-controlling value to the gates. That is the second step in the path sensitization. Next comes to verify the fault propagation through each gate. So this is like we can say it as a back propagation or backtrace method. For example, if the stuck at 0 fault occurs here, we have to assume the value to be 1 to check whether the fault is there or not. Is it so or not? We have to check it as, make it as 1. So when 1 is given here, output is 0 over G1. After inversion, it is 0. So when this 0 is propagating through AND gate, output is 0. So this should propagate and we should get through the Z. This is the step 1. So now assuming the non-controlling values to the other gates. For example, NAND gate, we have to fix it as 1. For NOR gate, we have to fix it as 1 here. So we are giving 0. Got it? So if this is going to be 1, this is not going to affect the data that is traveling through the fault propagation fault. Got it? So this is how we have to backtrace and set the value. So what will be the text vector for this case? X1 should be 1, X3 should be 1, X4 should be 1, X2 should be 0. So this is the test vector obtained by the back propagation method. This is how we have to find the test vector using the path sensitization method. Coming on to another example where a number of gates is more. So here also we follow the same methodology. First sensitization of fault propagation path, then assigning the non-controlling value to the other paths, and then backtracing to find the inputs that should be given to identify the fault at each and every location. For example, here it is considered as stuck at 1 at X3. So forward trace stuck at 1, if you look into the SA1 fault here, what we have to assume here, X3 should be set as 0 to identify the stuck at fault. So when X3 is set as 0, X5 and G2 must be set to 1, then the G5 output is 1. This G5 propagate through G7, G9, G8, G9, right? So the fault propagation paths are G5, G8, G9 and G5, G7, G9. So how these are going to affect the identification of fault location is the matter. So what we do is we backtrace and find the value of each and every gate. So to propagate through G7, G9 and G4, G7 and through this path, G4 should be made as 1. So this should be made as 1. So for this to be 1, X1 and X2 should be 1, 0. Similarly, G6 should be 1 because here X2 is connected over here also. So this is how we identify the value of X1, X2, X3, X4 and X5 when it is passing through G5, G9. So the value is 10001 as is the test vector for this case. For another path, similarly, if we identify X1 is independent, maybe 1 or 0, it's okay. All other values are 1001. So this is how we find the test vectors for the given circuit. So what is the disadvantage of this path sensitization method? So the thing is more than one path is to be sensitized at the time. If the scenario is like that, we cannot employ this methodology. So this is the drawback of this method, which can be proved using the circuit example that is given here. When more than one path is sensitized, we cannot identify the actual location of path using this method. Thank you. Thank you for patient listening.